Hi all, welcome back to Cracking the Fang Interviews. Today I'm going to be talking about a fundamental problem called clone a graph. This problem is very popular at Amazon, Apple and Facebook interviews. So the fundamental of this problem is you've been given a graph and you're asked to clone it, meaning if I give you a graph, again, just a quick reminder, a tree is also a subset of a graph. So if you're given a tree or a graph, you want to create another copy of the same and return this copy to the user. And the question is a Leetcode question. It's Leetcode 133. It's a medium question. I have the link to the problem in the description down below. And if you haven't subscribed to us already, please click the like button and also subscribe to the channel for exclusive videos coming from high-tech interview questions. So coming back to the problem, so we've been given this graph as an example, and every node here has two substructures. One is the value of the node, which is 1 in this case, and the other is a list of nodes which are adjacent. So for 1, the adjacent nodes are 2 and 4. So you'd have a list which point to node number 2 and node number 4. So I hope the concept of the problem is clear and what's given to us. So you're given this graph, you're given a value for each of the nodes and an adjacency list. So if you're at 1, you look at the list and you go to the next element, you'd go to 2. And I want to establish a fundamental concept here. Whenever you're given a graph or a tree, one thing I want you to think about is traversals. How do you cycle through this graph, right? It will help you search or clone or do whatever you need to do with the graph. It's a data structure given to you, and what's expected of you is to know how to traverse it, right? And there are many methods, to traverse a graph. The most popular ones, which we should focus on for coding interviews, one is BFS, which is breadth first search, and the other is DFS, which is depth first search. So let's think about it. So if you're given this graph, what you essentially want to do is make a clone of this and create the same graph, but it needs to be a deep copy. You cannot change this graph and return it. You want to create a separate copy. The way you could do that is you could either go depth first, go all the way, keep a sequence of scene nodes, mark this as scene, and so on, and create a new node, right, and work backwards. So I'm talking about depth first search here. So that is how it's going to look like. So you, as I said, you'll traverse all the way back and then you'll reconstruct from the last node onto the first node. That's one way. It's called depth first because you are essentially going through the depth, right? You're going all the way through and then constructing and coming back. The other way that I usually prefer is breadth first. You can also, one thing I typically used to think breadth first is circle or level order traversal. So if you are at level 0, you will be focusing on this. When you're at level 1, you'll be focusing on everything at level 1, which is 1 and 2. They are distance 1 away. And then you'll focusing on things which are distance 3 away. Distance 2, in this case 3. This kind of makes a little more intuitive sense when you're cloning a graph. But there's no reason that should stop you from doing it with DFS. I prefer BFS because it's iterative for one reason. We can write it as easily as an iterative algorithm. And it's more intuitive because you're doing level order traversal. You're starting at a node and sort of looking at its neighbors and working from there. All right, I hope this made sense. We'll jump into the code right here. So whenever you start, you're given a question of graph. As I said, the first thing I want you to think about is traversals. The choice is gonna be BFS or DFS, keeping it simple. And here we pick BFS, but you could also do the same with DFS as an implementation. The second thing I want you to do is have a template in mind to write BFS and then modify it. What I mean by that is we'll see in the question below. So here, so what the first thing we do is we maintain a hash table The reason we want to keep this hash table is we'll keep, for example, if we have a graph A, B, and C, what we'll do is we'll have a mapping from A to A prime, B to B prime, C to C prime, and so on. So this is the hash table for that. The reason we need this is because we are going to be going through this original graph and we'll map it to this new graph that we create, which is A prime connected to B prime and C prime. I hope this made sense. And you'll essentially return A prime towards the end, which is your start node. So you've been given a start node here. And, you know, as in plain old BFS, you start with a queue. You know, you put the first level that we saw in the previous slide, which is level 0 in the queue. So we'll put A here, you know, and while the queue has elements, you're just going to pop this element out of the queue. You'll go through all the neighbors of A, which is B and C, and if your neighbor does not have a you know, copy in the hash map, meaning if B and C are not present, you're going to create a new value here. So we'll create B prime and C prime, and you'll also add each of the neighbors, meaning since A is out now, you'll add B and C, which is level 1. So you started with level 0 and now you're going to add level 1, where the definition of level 1 is nodes that are one distance away from the previous level. You're going to add them to the queue so you can loop back and come back to them later. And what you'll do is you'll also add neighbors to A prime. So you'll in this node that you created A prime, you'll add the neighbors as B prime and C prime in the node, not in the hash table. Just want to make sure you understand where the structure of the node is you know, given to us already as part of the question. So the class node is given to you in the Leetcode question. So I hope the concept was clear. What we are essentially doing is, to quickly summarize, we have, you know, we first thing we thought about for cloning was traversal. The second thing was we took a template BFS implementation and we modified it to our use, which was cloning. For cloning, we also used a hash table to keep a mapping from A to A prime, every node to its clone. And in the end, we just return the mapping of the start node. So in this case, if we were given A, we are saying hash map of A, which is A prime. So we return the clone graph here. Cool. So the time complexity of BFS, this is standard BFS. The time complexity is going to be O of V plus E. And the space complexity, if you think about it, it's gonna be, if we have this graph like we do A, B, C, so at one point we'll have all the nodes at one level. So it's going to be some factor of V, because you're essentially putting your vertices of the graph. So where V is the vertices, E is the edges of the graph. You are essentially enqueuing in your queue A at once, or B and C at once, which is one level, which is some factor of you know, V. In this case, it's 2 by 3 of V, right? 2 nodes of all the 3. But since we ignore common so constants, it's going to be V, cardinal of V. Cardinal means numbers, so this is called cardinal again. I hope this made sense. Please like, comment, and share our videos. And thank you for watching yet another video from Cracking the FANG interviews. This is a very important Amazon question, and I encourage you to practice this thoroughly. We'll